So continuing this section, let me just tell you, we're getting into some a little bit more complicated calculations we're going to have to deal with. But let's start with this theorem, which tells us the solution to a 2 by 2 non-strictly determined matrix game. So the matrix game is defined by the matrix M. And let's assume that we're going to use optimal strategies P star and Q star, and the value of the game is going to be V. Okay, so P star would be using the probabilities P1 star and P2 star for the probability of, row 1 or row 2. And it's going to equal this, D minus C over capital D and A minus B over capital D. And I'll talk about this in a minute. Q star is going to be Q 1 star and Q2 star. This actually should be a column. Q1 star, a column, Q1 star, and Q2 star, not a row. So anyway, now, and it's going to equal, the first entry is going to be D minus B over capital D and A minus C over capital D. Now, and V is going to be AD minus BC over capital D. Now, capital D is defined to be A plus D and then minus B plus C. So that's capital D. All right. So let's apply this to our game. So let's say we have a matrix game M right here. All right, so we know A is 2, B is -3, C is -3, and D is 4. Now capital D would be A plus D, which is 2 plus 4, minus -3 plus -3. So we would have 6 minus -6, which would be 6 plus 6, which is 12. So capital D would be 12. So P star would be what? D minus C, so that would be 4 minus -3, so that's 4 plus 3, which is 7, over capital D, which is 12. And then the other entry would be 2 minus -3, which would be 5 over 12. So 7 twelfths and 5 twelfths, and that's what we got a minute ago. And then Q star, doing the same way, D minus B would be the same, and A minus C would still be the same, so it would be 7 over 12 and 5 over 12. So you can see Q star. And now V would be AD minus BC over D. So AD minus BC would be 2 times 4, which is 8, minus -3 times -3, so it's 9. So 8 minus 9 would be -1, so that would be -1 twelfth. So therefore, and you can see these match the previous results that we got. Let's apply it to another game. Let's say we have this game, 1, -2, -1, 0. So A is 1, B is -2, C is -1, D is 0. And so capital D would be 1 plus 0 minus -2 plus -1. So that would be 1 minus -3, which is 1 plus 3, which is 4. So capital D is 4. Now, going back to the formula for P star, I need D minus C over D and A minus B over D. Well, D minus C would be 0 minus -1, which is just going to be 1 over big D. The big D is 4. And then I do, to find A minus B, I would have 1 minus -2, which is 1 plus 2, which is 3, over capital D, so it would be 3/4. So P star would be 1/4 and 3/4. And then, but if we do Q star, we actually get for Q star, D minus B and A minus C, we're going to get 0 minus -2, which is 2 over 4, and then 1 minus -1, which is 1 over, let's see, that's 2 over 4 again, so we're going to get a half and a half there for that one. Let me clarify here we're doing D minus B, so it's 0 minus negative 2, so that's why we're getting 2 over 4, which is a half. And then we're doing A minus C, which is 1 minus negative 1, which is 2 over 4, which is a half again. So it's not the same numerators for the P stars and the Q stars, so the numerators are different. Okay, so we get 1/2 and a half here. And then for V, if we do the formula for V, AD minus BC, we take 1 times 0 minus negative 1 times negative 2, so that would be, let's see, 1, 0 minus negative 2. Actually, that should be what? That should be a minus, shouldn't it? It's a minus, so it's actually minus, it's actually negative 0.5. So V is a negative value. Okay, so anyway, that's how we can calculate these solutions to these games, these optimal solutions to the games. So it's a little bit confusing. You really need a whole course to understand this, but just trying to give you what I can in these sections here. Let's talk about recessive rows and columns. Some strictly determined and non-strictly determined higher dimensional matrix games may be reduced to lower dimensional games because intelligent players would not play certain rows or columns. For example, this game, it has no saddle value, so the game is not strictly determined. But from R's perspective, column 3 should never be played. Okay, column 3, let's see, from R's perspective, R would never play this column. Each element in row 3 is greater than or equal to the corresponding element's row. I'm sorry, row 3 should not be played, not column 3. All right, row 3. Because if you look in row 3, let's see. Okay, I had these two crossed up, so let me start over here. From R's perspective, row 1 should never be played. Because if you look at row 1, you've got the lowest values. Negative 3 is lower for R than positive 3 or negative 2. And same thing for 0. 0 is worse off than 1. So you really should never play this row, because you're better off playing this row if you're R. So either this row or this row, but not this one. So we would mark out that row. And then from C's perspective, C would be better off staying away from column 3, because he actually can, you see the negatives here, that means that C can gain something here and here, but over here C can't really gain anything. So if you mark out row 1 for R and column 3 for C, then you just get these values here. So basically you end up reducing it to a 2 by 2 matrix here. I may not have explained that greatly, but that's the idea, to reduce it to a 2 by 2 matrix. And then from that 2 by 2 matrix, you can do what we talked about earlier, and I'll just let you refer back to that, where we use those formulas to get P star, Q star, and V. And notice that P star is 3/7 and 4/7, Q star is 2/7 and 5/7, and then V is 1/7. So basically, a row of a payoff matrix is recessive if there exists another row called a dominant row, such that that element of the dominant row is greater than or equal to the corresponding elements of the recessive row. And that's what we had up there. We basically were just focusing on the dominant rows. And same thing with a column. A column of a payoff matrix is a recessive column if there exists another column called a dominant column, such that the element of the dominant column is less than or equal to the corresponding elements of the recessive column. Now, recessive rows and recessive columns may be deleted from the matrix, since intelligent players would never choose these rows and columns. So basically, we removed this row because this is a row that player R would never choose, since these rows you can get bigger values for R, and player C would never choose this column since we can get bigger values or smaller numbers here, more negative numbers in these two columns for C. Alright, let's see where I am here. Let's wrap this up. So let's solve the game by deleting the recessive rows and columns. Okay. M is not strictly determined, so I'll let you figure that out, but since there's no saddle value. All values of row 2 are greater than or equal to the corresponding values in row 1. So we can delete row 1. Okay? So, 0 is greater than -1, -2 is greater than -3, 4 is greater than 1, 0 is 0. They're equal. All values in column 2 are less than or equal to the corresponding values in column 1 and 4. So we can throw away column, let's see, all values in column 2 are less than or equal. Okay, well that's what I want. I want column 2, don't I? So column 2 is less than or equal all the values in column 1 and 4. So I can throw away those two columns. And then, so for C, the -2 is better than 0. And the -3 is better than 2 or 3. So in other words, you want these with the negatives in them for C. So that leaves us with these 4 values. And then you can calculate P star, Q star, and V using the formulas we gave you earlier. And now you get -1/5 or -0.2 is for the value of the game. Now, the game is a fair game and favors C. Why? Because V is negative. If V was positive, it would favor R. But since it's negative, it favors C. So we would say that R's optimal strategy is 0, 2/5, and 3/5. This means that player R, using a random process, should choose row 1 never with probability 0, row 2 with probability 2/5, and row 3 with probability 3/5. And then Q's optimal strategy would be 0, 7/10, 3/10, and 0. So never choose column 1, choose column 2 70% of the time, choose column 3 30% of the time, and never choose column 4. Okay? And if both players follow their optimal strategies, the expected value for R is to lose on average -0.2. I guess in terms of dollars that would be 20 cents. And then C would gain on average 20 cents per game. And then the last statement, even though dominance is applicable to strictly determined games, its primary use is for mixed strategy games. Mixed strategy games are easier to solve after they have been reduced. In the next section, we'll see how we can use an earlier topic to solve game matrices. We can return to the concept of linear programming. Great fun, huh?